Welcome to the video tutorials for SOFIA's Observing Proposal Tools. These videos should help you plan your observations and guide you through the program used to submit observing proposals on SOFIA called USpot. Further assistance is always available by emailing sophia_help@sophia.usra.edu. The first example I'm going to show you is the forecast imaging example. And here we've set up an observation. We're going to set up an observation for a star forming region called W40. And it's going to end up being a dual channel map of a small cluster of sources. The science case here is that typically with a lot of mid-infrared clusters in the sky, you have excellent data from Ys up to about 22 microns, but often people would like to have 30 or 40 micron photometry to supplement the Ys data. Or sometimes they just want to go deeper in the same bands as Ys. In this case, we're going to be trying to obtain 30 to 40 micron photometry for the sources in this cluster. The cluster is slightly bigger than the forecast field of view, so we're going to end up making a small map. Okay, so the first thing to do is to evaluate the feasibility of the observation. So the first thing to check is whether or not the target has actually been observed before by SOFIA. And you would do that by checking the DCS archive. We're not going to do that here in this demo, but you would search on the source name, and then with forecast imaging only, and if any results showed up, then you would need to carefully justify why you want to observe this target again. It could be a different set of filters, it could be much longer exposure time, and so forth. Okay. The other thing that you want to check is the reserved objects catalog to see if the object is on the reserved objects catalog. So I have a link here, and so we'll open up the link to the call for proposals. Now the call for proposals always contains the reserved objects catalog. And so if you scroll down through the table of contents, you'll see at the end the appendices. And here you can see there's an ROC for both GREAT and FIFI-LS, but not forecast. And so we're safe. So there are no reserved objects for forecast for cycle 8. Now if there were a forecast catalog of reserved observations, you would have to check that specifically here, and it can show what the catalog basically looks like. It gives you a list of targets, right ascension declinations, the approximate extent that's reserved, and what lines, in this case, are reserved. Okay, but we don't have to worry about that for our observation. So the next big question then is what filter set to use. What filters do we want to use? Ideally, we'd like to pick one around 22 microns to anchor our data to the WISE data at 22 microns. And then we'll need one past 30 microns to actually do our science. So the place to start is table 4.2 from the Observer's Handbook. And I have a link here to the Observer's Handbook. And when you're using the Observer's Handbook, make sure that you're using the one for the current cycle. In this case, it's cycle 8. Okay. And so we come down and take a look at the performance and the filter suite. So remember that forecast is a dual channel instrument with a short wavelength channel and a long wavelength channel. And in dual channel configuration, we can use a dichroic to split the incoming beam, which allows us to observe at short wavelengths and longer wavelengths simultaneously. So, or you can run in either in single channel mode in either the SWC or the LWC. Now, the important thing about using the dichroic is that if you do, you take a hit on throughput. So we're going to come back to that in a minute. Let's first identify what filters we want to use, and then we'll assess whether or not we want to try to use the dichroic. Okay, so first, to since we're trying to observe faint sources, we'd like to use the most sensitive filters that we can, which basically translates to filters with very wide band passes in general. And so for our observations around 22 microns, we want something that's close to 22 with a wide band pass, and probably the best choice is going to be the 19.7 micron filter with a band pass of about 5.5 microns. You can see here the effective wavelength of each filter and the approximate band width. Now for our 30 to 40 micron filter, we have a number of possibilities here from 31 to 37. The widest is the one at 31 at 5.7 microns, and but the 37.1, the 34.8 is also a good choice at 3.8. We'll go with the 31.5 in this particular example, though your science may require you to pick something a little bit further to the red. Okay, so we have our two filters, a 19.7 micron and the 31.5. And so that brings us to the question of whether or not we want to use FORCAST in dual or single channel mode. Now, obviously, the advantage of using FORCAST in dual channel mode is that it reduces the amount of time. If you're using two filters, it reduces the amount of time that you need to observe by approximately half. The disadvantage is that you take a hit on throughput with the dichroic in. So in the 11 to 25 micron range, the throughput hit is down to about 85%, whereas at 25 to 40, you go down to about 40%. So what this means is shown in the sensitivities chart here. And so you can see that for our filter sensitivities for each channel, there's a sensitivity for the single channel mode, and then a sensitivity in dual channel mode when you're using the dichroic. So you can see for the 19.7 that the lower limit on the, and I believe these are 4 sigma 900 second observations. So this would be a, it doesn't, yes, here we go. So this would be a minimum detectable continuum flux at signal noise of 4 and 900 seconds. We don't care so much about the details of those numbers. We're more concerned about the difference between each lower limit. So in the case of 19.7, you go from 73.5 in single channel modes to 77.4. So that's not very much. That's a small hit in sensitivity. However, for the 31.5, you can see that you go from a minimum continuum detectable flux of 126 out to about 171. So you do take a significant hit at longer wavelengths, but this is more than made up for the fact that you'll be able to double, in a sense, be able to double your mapping time because you can observe both filters simultaneously. So we'll go ahead and use FORCAST in dual channel mode. And so now what we want to do, now we have all the information we need to calculate the integration times for the 31.5 micron filter. First, you need to justify what your sensitivity limits are. So in our case, we're going to want to make 5 sigma detection in 31.5 at a flux limit of about 0.2 Janskis. And these numbers have to be justified very carefully in your technical section. Your 5, you might justify 3 sigma, you might justify 10 sigma, you might have a lower flux limit here, a higher flux limit, whatever. Point is that it all has to be justified in the technical section. But once you have your choice of filters, you've answered the question of whether you're going to use FORCAST in dual or single channel mode. You've established your sensitivity criteria. Now you can actually go to the SOFIA integration time estimator site and actually run those numbers to find out what your total integration time is going to be. Okay, so here's site, and you can see it opens up directly to the FORCAST imaging time estimator, and you simply just have to go through the different fields and select specify your selection. So here we're going to be using the F197 and the 31.5. We're not interested in signal to noise ratio, we're interested in total integration times. We want to achieve a signal to noise of 5. And we want to, and since we're going to be primarily interested in the 31.5 micron filter, we're going to have a flux limit of 0.2 Janskis. Now down below you have to establish your observing condition constraints. This is because SITE uses a atmospheric transmission model, ATRAN, and convolves it with the filter profile to give the most accurate sensitivity estimate across the band. So, so in general, we recommend that you don't change from the defaults unless you really have very specific constraints for your observation. So the defaults are the 40 degrees in telescope elevation, 41,000 feet altitude for the aircraft, and a 7.3 micron water vapor overburden. Okay, so once you've specified all your constraints, go ahead and hit calculate. And you can see right at the top the integration times required for each band. And so for the 31.5, and of course the 19.7 is first, and the 31.5 is second. So you can see that you get an integration time of approximately 9 minutes. Now, so that's good. You want to make sure that your integration time is not much smaller than that. You also want to make sure it's not many hours. In general, the integration time should fit comfortably onto a typical SOFIA flight leg, which is anywhere from 15 minutes to a few hours. Okay, so for completeness, if you want, you can actually, since we're going to be observing in dual channel mode, you can actually go back to the time estimator and figure out what the flux limit would be at 19.7 for 5 sigma with 9 minutes. But I'll leave that, but that's not required at this point. Okay, so the feasibility looks good, and so the next step would then be to take the details that we've worked out so far and enter them into USpot. Okay, now that we have established that the feasibility for our target looks good, we can go ahead and open up USpot and start creating our AORs. So first we go to the launcher to find USpot, which we've already downloaded and installed. And the first thing we're going to do once it launches is we're going to create our main target. All right, click the tip. And so here's the USpot presents the proposal in 2 panels. There's the main proposal information in one panel that has things like the title, of course, the various proposal information, keywords. This is where you attach the PDF, for example, abstract goes in here and so forth, and also the investigators. We're not going to be going through all these. This tutorial is, this example, excuse me, is mostly about how to detail your astronomical observation requests. The AORs are over in the observation panel. Since this is a brand new proposal, there's no AORs in the list yet. So the first thing we're going to do is we're going to create a new target. With the new target panel, we'll do a, so let's see, get W40. We'll resolve it. There we go. So we can see we got the right ascension and declination from Sinbad, and click OK. Okay, so now that target is available for use, and you can create as many targets as you like for your particular proposal, and then select them for each AOR. So now the next thing we're going to do is we're going to download a WISE image with a 30 arc-minute field of view for our target. So the first thing we do is go to Images, pick a WISE image, and we'll use the 4-band Atlas. Band 2 should be sufficient. It's around 12 microns. And here, though, we want to reset the field of view to about 30 arc minutes, give ourselves a little more breathing room, and click OK. So now we'll see a new panel is opened up down below next to our observations for W40. And so you can see it's a very bright H2 region. And the cluster that we are interested in is right down here in the middle. And so we can, there we go. Okay, so now that we have our background image and our target set up, now we can make our first AOR. And the way we do that is by clicking Add AOR or Create AOR. We pick the mode, Forecast Imaging. And so here, so this is the main AOR panel for Forecast Imaging mode. And keep in mind that for the Phase 1 proposals, you only need to specify the data that's, or the parameters that are identified with the red asterisks. Now we're going to specify a few others for completeness, but only the ones in red are required at this point. Okay, so the first thing we're going to do is we're going to give our AOR unique label. So we're going to call it W40 app.1 in the expectation that we're going to probably make a small map here. And so next down, so you can see the AOR has picked up our target automatically. Next, we're going to specify the observing conditions. We're going to specify the exposure time. This just comes straight from the exposure time estimator. So here, you can put in. We're just going to round up in this case from 9 minutes to 10 minutes. Okay, and then the configuration of the instrument we're going to set to dual. The short wavelength camera will be using 19.7. Long wavelengths will be using 31.5. Okay. So the next question is what chop nod style to use. There's three choices. There's nod match chop, which is the default and is the most common chop nod style. There's a perpendicular chop, and then there's also C2 and C2. So the way that you determine which one of these to use is to first overlay our AOR onto our map here. So what we're going to do is go up to the overlays, pull down to current AOR. And now you can see the red box here represents the central field of view for the on source beam. And then the blue and green boxes represent the off beams. So you can see here in nod match chop mode that with only a 60 arc second chop throw, that you're not even really chopping completely off the cluster. So we need to increase the chop throw. But furthermore, the larger issue here is that even if you increase it to say, 200 arc seconds, you're still not going to be able to chop off to blank sky, no matter where you end up, no matter what configuration you put in here for nod match chop. You're going to end up getting some of this nebular background included in your off beam, and that's going to be a problem for your background subtraction and ultimately for your photometry. So in this case, when you can't get completely sky off beams, we recommend using C2 and C2 mode, which allows you to sample the sky nearby free of nebular contamination. And so let's do that. So let's set that up. So in this case, we're going to put in a nod throw of 600 arc seconds and a nod angle of 90 degrees. So we'll switch to C2 and C2 mode. And we will switch to a nod throw of 600 arc seconds with a nod angle of 90 degrees. So what this will do here now is you'll see that your primary beam is still here on the cluster. Your first off position for your first chop position, sorry, is shown here in green, which is relatively free of nebular emission, but not completely. And then the telescope nods off to a blank piece of sky, in this case over here, and chops again. And so hopefully this area will be pretty much completely free of nebular emission. In fact, we could probably move it up just a little bit to get it off this little bit of emission here. So what that does for you is allows you to get a very clean sky background for your double differencing. And the problem, of course, is that you take a huge hit in efficiency here because your target is only included in one out of the four beams on the sky. So, and you'll see that in just a moment. So, but you get a nice measurement of the background, so this is definitely the preferred mode. The other advantage of using C2 and C2 is that your chop type is asymmetrical, and that gives you the best image performance for your on beam, right? It's on axis. It's relatively free from coma. Okay, so let's just click OK on that and take a look at the observation. So now you can see we have an exposure time of 10 minutes here. So my exposure time is not correct. The exposure time should be 600 seconds. Imaging dual, 19.7 micron, 31.5 micron in the long wavelength filter, C2 and C2. Let's click OK. There we go. So now we have an exposure time of 600 seconds, but notice, which is approximately 10 minutes, but notice that our total duration now for this one observation is approximately 53 minutes. And that's because we're using the C2 and C2 mode. Okay, so the next thing we want to look at is the mapping parameters. So here you can see that the cluster is just slightly larger than the forecast field of view, and so we want to lay out a small map. And the easiest way to make a little map is to simply so the forecast field of view is approximately 3.3 arc minutes square. So it doesn't cover the whole cluster. But note that the detector angle is not known prior to the execution of the observation. So you have to plan for any arbitrary detector angle. So it could be, you know, at about 45 degrees here, it could be at 0 degrees or minus 45 degrees and so forth. And so you have to plan ahead for the possibility, for any of those possibilities. The easiest way to do that is just to calculate the map points by using the following little formula. The field of view for forecast, 3.3 arc minutes, divided by the square root of 2, which gives you a separation between each map point of about 2.33 arc minutes. So if you take the size of the field of view and divide it by about 2.3 and then round up, that gives you the amount of map points you need. So for example, for a 5 arc minute by 5 arc minute map, which is approximately what we're looking at here, would require a grid of about 2 by 2 map points, or 4 positions. So the important thing to note about this is that at this point in the phase 1 proposal process, you don't actually have to create all the mapping positions. That can wait until phase 2. You just need to know how many map positions are needed. And since you're going to need 4 map positions, what the instructions in the handbook indicate is that you need to create, let me go back to my observation here. You use the cycles to indicate how many map positions you want. So each map position is going to be observed for 600 seconds in dual imaging mode with C2 and C2 chop nod style, and you're going to do that for 4 map positions here. And so you click OK to update. And now you can see that we went from a 50-minute observation to a 212-minute observation. This is the total requested observing time. And what you want to do is you want to compare this total time to typical leg lengths of 15 minutes to a few hours. So you can see that this is more than a couple of hours, right? So this is 3.5, almost 4 hours of observing time. And so it's very likely, so you're not going to get all of this time onto one leg. It's very likely that each map point will get broken up onto a separate leg. Okay, so that's the end of example number 1 for forecast imaging. And next up, we're going to take a look at a forecast GRISM observation.